Nigeria and Sagu are insufficiently Italian. Welcome to part 3 of a walkthrough of finding neurons in a haystack. We spoke at length about random access definitions and compound word detectors. Now we're going to talk about our next case study of contextual neurons. Want to give us an overview, Wes?
Yeah, so based on our previous discussion on superposition and the potential efficiency gains, I think it's natural to ask, like, maybe this is just like so beneficial for models to like use the superposition to represent all these different features. And so should we like ever expect individual neurons to be meaningful, right? Should, a one sparse probe ever actually be useful? Neil discussed the sort of different types of interference and also sort of different types of being simultaneous and alternating, and also different types of features where you could have binary or mutually exclusive features like n-grams, which are much simpler. But we hypothesize that contextual features, which are features which describe some large portion of the input, so like the actual language that the text is in, or maybe the programming language that some code is in, that these features would be so important that any interference on them would really degrade model performance, that these were really important to like get right that you were in fact in French. These features are also like a little bit more complicated to detect. So, as we were discussing for the social security feature, so for compound words, it's very easy to detect if the current word, if the current token is security and the previous token was social. In contrast, these, contextual features are maybe much more subtle. So, you can imagine detecting programming languages. There are sort of many more sort of common keywords. Code can look roughly the same. There may be different stylistic conventions, but in general, it's much more subtle while being more important. And so we hypothesize that these traits made these contextual features more likely to be represented compactly by like individual neurons. And so concretely, the setup here is we had a data set of French text and not French text or all other languages. And we tried to train a classifier on the average activations across the whole sequence. So rather than on a particular token, this is an average across the whole context. And when we trained probes to do this, we found these individual neurons. And this particular plot now is not for the average activation across the whole sequence, but on literally every single token. And so what this shows is that this individual neuron, neuron 609 in layer 3 of Pythia 70M, seems to activate if and only if a token is in French. One thing which you can do is then break this down by the individual vocabulary units. So just to maybe go over my axes here, this is the pre-activation. So before we apply the JLU for 3 different neurons, this first one being French or not.
Presumably pre-activation because I don't know, everything below 0 gets set to about 0, so it just looks kind of dumb.
Right. Yes. This plot would look much less pretty if you applied this post-activation, but sort of it would imply the same result.
How many hours did you spend making this plot look pretty?
This one was many, many, many hours. In particular, like making the tick sizes different and like the spacing, just like this is not default matplotlib. This is and also the Neil was quite insistent that the boxes be aligned on top of each other. This is also not a matplotlib default, and so required a significant amount of tuning, and also just like getting the exact width ratios of these plots to be exactly how I wanted them. I believe it's like 1, 2.5, 1.25, I believe is the exact ratios. Getting the grid lines just right, having the space. Yeah, anyway, it was a mess. It was a long time.
This is the level of dedication Wes has to producing a great paper walkthrough.
Well, great paper. I don't know about the walkthrough.
It's fantastic.
But so
if anyone, we can call it fantastic because if anyone gets this far, they've
right. They clearly wanted it. So what is this middle plot saying? So this is now giving us the breakdown of specific tokens. So this is the activation of the interface token when it's in Go code versus other types of code. I think the mental model that I get from this is that these neurons, among other things, are playing a role of disambiguation. So despite the return keyword appearing in many programming languages, or the assignment operator appearing in many programming languages, this particular neuron only fires on those tokens when they're in Go versus not. Maybe the most compelling piece of evidence is, okay, I have this French neuron. What happens if I just delete it? If I always just set the French neuron to 0, what happens?
We didn't even do sensible fancy ablations, but just like, fuck it, 0.
Well, but I mean, based on the activations, it's basically just yeah, it would always just be setting it to 0 anyway. So you can ask is, well, okay, if I sent this French neuron to 0, what actually happens to the language model's performance, right? So a language model tries to predict the next token. We can just measure how good it is at predicting the next token when you delete this neuron versus not in different contexts. And so what you see is if you delete the French neuron, loss goes up by quite a bit. Just the single neuron loss goes up by quite a bit when you're in French, whereas basically all other languages remain unchanged.
Note the x-axis on the right of about like 8.
This is now the loss increase over the whole sequence, and this is the distribution thereof. And this is fairly mediated by model size. So, the 70 million parameter model only has like 12,000 neurons. And so when you delete one, it's like a 8 or 9% loss increase on average. Whereas in the 7 billion parameter model, it has like, I think 524,000 neurons. The loss increase is much more modest.
Oh, 0.2, still pretty big.
0.2 is still pretty big, yeah. And just for reference, USPTO is US patent documents. And so the model, the pythia models are trained on the pile, which is this data set, which has it's kind of an ensemble of different sources. It includes Wikipedia, archive documents, various like legal documents, and US patent documents, among others. And so in addition to like the natural language or the programming language of specific sequences, we also tried to find context neurons that activated for specific subsequences of the pile. And you can imagine that these neurons are potentially interesting from an alignment perspective, because these neurons, you can make a fairly trivial like in training classifier if you have a bunch of these like neurons which activate for specific subdistributions of your training distribution.
Note, this is an extremely contrived example. I do not actually think this would be useful.
Well, I mean, you could imagine though having a neuron for each of your subdistributions, and then the sum is just like whether or not you're in training or deployment.
A plus version of this, maybe.
Right, but it's still interesting as a minimal precursor.
So we should also give an explicit shout out to Elutha, who both trained the Pythia models, I think led by Stella and Haley, and created the Pile, I think led by Leo Gal, who's now at OpenAI.
Yes.
So appreciate it. The Pythia models, I think, were intended to be for studying training dynamics and data stuff, which I'm not that interested in. But they're also just like a really good suite with good scaling properties that are actually trained on code and interesting stuff and on multilingual.
Yes.
So, appreciate it. Thanks. Maybe another fun question. So French, Go, and USPTO are interesting things to search for. What's the story behind why we ended up with these?
So as we mentioned, a big limitation of probing is that you need a labeled data set. And so a lot of the like features which we studied were sort of guided by what types of features would be easy to get supervision for cheaply. And so one of the things which the Pile was trained on is European Parliament documents, which are very kindly annotated with the host country and therefore what language they're in. So this supervision was given to us almost for free in terms of you just looked at the metadata of the sequences from the Pile that were in Europarl. And so that gave us a nice classification task. Similarly for like USPTO and other Pile classes, again, this was just like very easily in the metadata. And so this was like pretty trivial to probe for. Programming languages was like slightly harder, but we used some external package which like recognized what programming language something was from. And so we took a bunch of archive documents, or sorry, a bunch of GitHub sequences, ran it through this, and took the ones which with highest confidence, and used that as a data set.
Really? Huh.
Yes.
That's less compelling than I thought. I thought we just had some labeled data.
No.
Definitely sources of labeled data.
Wait, why is that less compelling?
Well, so if we're filtering for things that our program is highly confident would go, what do we do with the stuff that it's not sure what it is?
Well, so the problem is that like a lot of these, like if it's not confident, then it's probably like some file with like just a bunch of comments in it, which is like much less interesting from like a code recognition point of view, right? Like if you think about like some C++ header file, which is just like mostly words, it's like, well, okay, sure, this is C++, but like, you know, you'll notice actually in this with this Go neuron that there's like this tail of activations which are below 0. And so it's like, well, even though there are very few things that are not in Go which cause this neuron to fire, there are many things which nominally are in Go which cause this neuron not to fire. And the story here upon observation is it seems like these are mostly like comments. Like a Python neuron will not fire on a Python comment. And so this is like one concrete example of, you know, your ontology probably does not match to the network. Like the network isn't literally just like, is this in a .py file, right? It's a little bit more just like, okay, is this actual like executable code within that executable Python code is like maybe the true feature here, right? And so it would not fire on comments. And so this data cleaning procedure was to try and prevent those sort of confounding factors.
Yeah. So if there was something where it wasn't sure what it was, would that go on to not or be discarded?
This would be discarded.
Makes sense. Thanks. And yeah, maybe a broader point here. My understanding is this project was in some sense bottlenecked on just making a bunch of data sets. And how many data sets do you make in the end, Wes?
So make is maybe a strong word in the sense of like the USPTO, like you basically just had to like look at some metadata and like, yeah, get it in the right format. But in total, we had like maybe 10 or so like overall feature classes, each of which, but many of these were categorical, and therefore we ended up probing for like over 100 different features. And so this was quite a mess keeping this all straight. And yeah, it was generally just a more tedious part of this project was making the data sets and just, yeah.
Yes, which is also just kind of generally an issue with probing. You both need to know what you're looking for, but also have a bunch of data that is labeled. I also think it's a point of failure for me as a mentor that I did not stop Wes from his dangerous dataset creation addiction.
Yeah, it got me lots of interesting things to study. And I also think that like, you know, it is bad that you have to do this, but like once you have a probing data set, you can just reuse it. And so I think, you know, even though I would not want to live in a world where we're relying on probing to like, you know, find like really alignment relevant features, I still think it's reasonable to have probing data sets which like correspond to features of interest, just as like an initial first pass of like finding things which are at least correlated and, you know, can generalize between models without too much retooling.
I'm also really curious. There's like this dot above like HTML and JavaScript and Python, and I'm like, the fuck is that dot?
So these outliers could definitely like, especially with HTML, I could totally imagine some like embedded Go code within like some HTML, or it's just like a web page document that like has that like is actually just a Go tutorial and like therefore has some amount of Go code within it. Another thing which is like hard with code is just, yeah, it's not always cleanly delimited, and yeah, there might like, depending on, you know, what piece of a file you get, you might be getting like a good chunk of the license, and like, yeah, there's just like all sorts of confounding things here, but these would be interesting to look into.
Makes sense. I think I recall you saying you tried searching the pile with regexes for things like hexadecimal and decided it was too fucking cursed.
Yeah, so it turns out with probing, it's fine if you miss some things from your positive class. But if you have actual negatives in your positive class, labeled as positive. This is like quite harmful for probing. When you're doing like a regex thing, if you cast too wide a net, yeah, it's just quite bad. And like hexadecimal, there's like many things which like match just like a simple regex for hexadecimal.
Can you unpack why false positives are more of a big deal than false negatives?
Right. So this has to do with the sort of prevalence of features. So your negative class typically involves a bunch of stuff. And so even if there's like a positive example in your negative class, it's probably going to be much rarer than, you know, the full sort of gamut of all negative stuff. And therefore the relative ratios of negative things, or sorry, of positive things within your negative class is likely to be quite small. However, if you cast too wide a net, it's likely that the things which are not your true feature sort of outnumber your true feature and therefore account for like a non-trivial fraction of all your positive examples. And then you're actively probing for something which is not the thing you're looking for. So I think it's a claim of like frequency within the positive and negative classes.
Interesting. So like you're probing for some feature like French, and you've got a data set of 20 languages, so most are not French. So French occurs 5% of the time. If you misclassify like 20% of the French, that's only like 1 out of 95 of everything else, which is basically nothing. If you instead, for every like 5 bits of French, get 1 bit of something else, because there's so much everything else, you're going to get drowned out.
You'll really poison your positive class. Especially a problem with regexes, because often the pile is just so much internet text. And, you know, for any actual like regex that you can make, you'll be surprised at all of like the random crap which can activate for it.
You have any favorite examples?
Oh God. Or it's just like you can imagine like, you know, doing something for phone numbers, but like actually there are like lots of, you know, random things which have similar numeric representations where like, you know, even you have even if you like only look for things with like dashes or like parentheses around the area code, like you'll still get lots of random crap. And yeah, I was surprised by how difficult this was actually to do.
Random numbers feel so easy. I
I
should go
know.
try this.
Yeah.
So returning to this, I think the methodological stuff we're on is kind of an interesting thread. Do you want to say more about how exactly you trained these probes? So, like conceptually, it's kind of hard to think about how you train a French probe because French is not a property of a token, it's a property of the text. But each token
Right.
has its own neuron activations.
Right. And so for anything which is not a property of a single token, you often need to apply some sort of aggregation to the activations. And this is somewhat driven by just intuition and judgment. So for contextual features that are sort of by definition apply to lots of tokens, we can just average across the whole sequence. And you know, you can see within French, even if you take the average, these will sort of be centered at these histogram means. And so you will get like a lot of separation.
Sorry, just clarifying. You take, say, 100 French texts and 900 non-French texts.
Right.
You get 100 data points for French, which is the average of the residual streams, and you train your probe purely on that.
Average of the neuron activations, average across everything within the context. So, you know, if you have like 512 tokens for each of these 1,000 sequences, you get 512 by of the neurons matrix, and then you average over the sequence index and then get a vector, which is just the number of neurons per each sequence. This gives a somewhat weaker result because notice this would not distinguish between like, is French noun versus is French adjective. From the view of the probe, you know, assuming nouns and adjectives happen about the same, this is like, would not distinguish between these two cases. And so when you do this sort of average activation, you do need to do a second pass of like actually more rigorous analysis of what the feature is. You could also imagine doing a max aggregation. And I think that this is most appropriate for like features that are for small token span. So you could imagine anything having to do with names. This is almost always going to be multiple tokens, especially if it's a first name, last name. It's definitely going to be. And here, you're maybe not sure where exactly the like feature gets computed, although some results from the Rome paper and others sort of suggested that maybe the last token is like sort of uniquely privileged in this sense. But you could just take a max over the neuron activation, the max over the neuron activations of the tokens which span this like feature of interest. In this case, maybe a name or like a country or city name or etc. Yeah, this has less problems with weakening, although the problem gets bigger as the token spans on average get longer, because there are more possible things that you could be aggregating over.
Makes sense. And so the histogram in the top left, we identified the neuron by only looking at the average across the French text. It could easily have been a French adjective or French noun neuron, but the histogram is by token, and every token in the text is a separate data point. So the clean separation shows us that despite looking for like average, we actually found a per token French detector, which is like surprising and non-trivial.
Exactly. Yeah. And so this was only, but you did have to do this second pass analysis to actually find this and conclude this.
To my eyes, this paper isn't even really a probing paper. The story of this paper is we did probing, it found us some fun stuff, and then Wes went and did a lot of labor-intensive case studies doing a bunch of ad hoc, interesting follow-up. Like, if you look at the 3 graphs here, none of them are probing graphs. We have a spectrum plot of what the probe tells you across the full data distribution, the Europol data set distribution, we have analysis by token, and we have causal interventions and ablations. And just probing on its own, it's just too blunt a tool. It doesn't tell you that much, but it's a useful tool in your toolkit as part of a broader investigation.
And sparse probing in particular has advantages for localization, because rather than just getting this dense activation vector, which maybe literally has a coefficient for every single neuron, this can localize individual neurons, which are useful and like interesting and worthy of follow-up analysis.
Yeah. So maybe from a methodological perspective, suppose someone's listening to this and they're like, oh my God, Wes, you're amazing. I want to take your techniques and apply them to my own problems, or I want to go build 20 data sets to one-up you and do sparse probing on those.
Yes.
What are non-trivial methodological problems they might run into that they should know about?
Yeah, so I think dataset creation is very hard. So many past probing studies have been on what I'm calling, exhaustive and mutually exclusive features. So like this is like part of speech, for instance, where every token, let's assuming it's in natural language and not something else, like it has a part of speech, and therefore your set of negative examples becomes quite easy because it's just distinguishing verbs from nouns and adjectives and whatnot. And because it applies to because every token has this feature, it's just easy to construct this data set. For other types of features, you need to be careful based on the sort of relative frequencies of your positive class with like other possible correlates, which might be interesting. So maybe as an example, let's think about like probing for email addresses, right? So like this like you could hope has like a fairly easily regexable form, such that you could like create your positive class without too much trouble. A problem here is that all email addresses kind of look like URLs, right? In the sense that they like have .coms or .orgs or whatever. And depending on what if you use just like all random tokens for your negative set of examples, there are probably not going to be very many like URLs within your set of negative examples. So when you probe for this as email feature, you might actually just find like a URL feature, right? All that it does is just like look for .com or .edu or .org or whatever. So the lesson here is that you need to be very careful with what is in your negative, with what is within your set of negatives. So, if you are actually looking for very specifically email features, you'd probably want to make sure that there were lots of examples of URLs or like other things which sort of looked like emails but were not emails in your set of negative examples. Otherwise, you can just pick up on some correlate of emails, which is sufficient for the classification task, because like most random internet text like does not look like an email. And so, you'd want to include things with like URLs, random other things with like the character, et cetera, et cetera.
Let's say there is a URL detector that's also a reasonably good email detector. Why is that not just fine? We found an email detector. We can go home.
So yeah, it depends on the actual feature of why this is problematic. If you're making some like strong claim about what a model is like will or will not do, and it's based on like this neuron, which is sort of a URL detector but also sometimes an email detector, you can fool yourself in how it affects things downstream in a way which for important features could be more important than distinguishing between email and URL. In interpretability, we want to be careful about how we map our own ontology onto the networks and like making sure that we're actually understanding things as the network does and not just as we do.
Where ontology is like the structure of concepts through which we see the world. Like a tree is a thing rather than, I don't know, each leaf is its own thing and a tree is like a cluster of leaves or something.
Or the average of a tree and a cat is like not in and of itself like a distinct concept which we care about, right? We care about trees and cats individually, but not as like some weird average. So I think that this depends on the actual example of like what feature it is, and I think that this could have, yeah. But in general, just like epistemics of interpretability, we want to like not be fooling ourselves with like our understanding of different concepts. Do you have an answer for that?
Yeah, I broadly vibe with everything you said. To me, the key thing is that I am a mechanistic interpretability researcher. I am trying to reverse engineer a network. This means I want to be doing causal interventions. I want to be understanding the internal mechanisms, how things fit together, and how all of this works. And to me, probing is very much a first step and a preliminary tool. And the thing I actually care about is how the model wants to represent email internally in order to use it downstream. And knowing how to extract it from the representation is like a naive first attempt to figure out how it uses it. And a URL detector is used for URL stuff, not for email stuff, even though it correlates with the email feature. And like this correlation causation distinction is like a very important part of what I think we need to be thinking about here. So I guess resuming out and summarizing the methodological thing, it seems to be the features we're looking for are very rare, which means we get a big imbalance in class size, where most things are not emails. And there are other rare features that are correlated, like URLs and emails. And if we don't have enough URL, if we don't specifically have a tranche of URLs in our probe training dataset, then we're just going to get basically no URLs as negative examples. And our probe isn't going to care whether it's got a URL neuron or an email neuron or both.
And so, yeah, I think at this point, maybe it makes sense to talk about some of the things which you can do to like as second stage verification tools. So obviously there was the causal ablation things and the context neurons. I think, yeah, causal investigations are like maybe the gold standard in terms of like actually verifying interpretations.
Well, causal interventions are better than probing. We can be so much more ambitious.
Okay, so what would it be? Like designing something from scratch and then plugging it in and seeing if it is that your
Yep,
gold standard?
it's pretty good. Yeah, like the curved circuits paper, they just thought they found curve detecting neurons, and they hand coded the weights from scratch, and it worked ish.
Yeah.
And I'm like, that's fucking impressive.
Causal intervention is the silver standard.
Bronze.
Bronze, okay. But like the anatomy of neurons give us like a few additional hooks on sort of what a neuron could be doing. And so Yeah, so one such hook. Okay, so just to describe the setup briefly, we were looking for neurons which distinguish between different types of athletes. So in this case, soccer athletes versus basketball, baseball, football, or hockey players. And we found all of these neurons, which in and of themselves were like very good classifiers individually of whether or not a particular athlete played the sport in question. And concretely, just methodologically, we train these probes on the max activations of the athlete's surnames, so their last names. And indeed, so we found these neurons, and then when we looked at what these neurons activated on over a wider range of text, this rightmost plot shows the value of the average activation for each token for these individual neurons. And you can see that they're like very sport aligned. So the soccer player detector neuron also just like activates for all of these words which are very associated with soccer. So like striker, header, kick, midfielder, etc. And likewise for baseball, where you have stolen, run, pinch, walked, football, wide receiver, defensive end, punt, coordinator.
Note that if you're from a civilized country, it's football and American football, as you were.
Yes, right. Football with your hands. The notable exception, however, is the hockey neuron, which seems to actually just like activate for all things about Canada. So Quebec, Canadian, Winnipeg, oil, maple, which I think is quite cute. But I think the story here is that, within your data set, if you're only sort of looking for things of, does this athlete play soccer versus not, there's like all these other degrees of freedom of things which could correlate with soccer as like a feature. And therefore, again, it's just a lesson in having to like actually look at these neurons in more detail after you just probe for them. But this is like one simple way of understanding what neurons do rather than just like max activating data set examples. This is slightly more robust where you look at max average activations of vocabulary elements. So, we didn't look into too rigorously, and there could definitely be other things which these neurons are doing.
Did you do anything to control for niche tokens that just had very few instances?
Within this?
Yeah.
So I think I only included examples with with count greater than like 5 or 10 or something. So again, when we think about like the anatomy of a neuron, it has an input weight, which it literally just dots with the residual stream after a layer norm. Then you have your post activation, and then you have your output weight, which is literally what is written to the residual stream. And because the unembedding is just a linear map, you can look at how much each of these output vectors for each of the neurons increase or decrease the logits of the next output token. And so this is another mechanism of sort of understanding what a neuron is doing.
And importantly, this is heavily related to the technique of direct logit attribution, where you take some activation and map that to the logits. But here, this is purely static. This is just weight-based. Right. Is that right?
Exactly. Yes, correct. And so, if you have a neuron which is, you think does a particular feature, so here, these neurons in 3 different pythia models are detecting the end of a sentence. We know that, whenever a sentence ends, the next token is usually capitalized. So as a hypothesis for this particular feature, to sort of like verify that these neurons are like actually, doing the ends of sentence or like actually corresponding to the features which end sentences, we can, look at this dot product between the neuron output weight and all of the vocabulary elements, and then split them by whether or not the token is uppercase or lowercase. And we would expect for tokens or for neurons which actually react to the ends of sentences, they will increase the probability of next tokens that have an uppercase that begin with an uppercase letter and decrease the probability of those with a lowercase letter. And so indeed, that's what we observe. In all cases, it's usually instructive to look at like actual concrete examples and like the tails of various distributions which you're looking at.
All summary statistics will lie to you.
Yes, indeed. And so what we have here are heat maps for two of these different neurons, where the columns represent this. So this column are the uppercase tokens with the greatest increase of logit difference. These are the uppercase tokens with the greatest decrease in logit difference. And these are the lowercase tokens with the greatest increase in logit difference. And so the interpretation here is that like the tokens which increase in probability the most are those that like often begin sentences or paragraphs. So like, or here are also things which maybe begin like sections and like in an archive paper, right? So like conclusion or discussion.
Do you remember whether these have preceding spaces or not?
I do not remember.
Fair enough.
They should. Yeah, I don't remember.
Makes sense. I quite like processing things to have dots if they have spaces, no dot if not, or something.
Yeah. No, I think that's important for especially if you want to conclude.
Yes.
Yeah. But I think this neuron's a little bit more clear where like, however is a very common way to begin a sentence or similarly, alternatively, right? These are words that very frequently begin sentences and so therefore would make sense to increase the most. In contrast, there are these other types of tokens. Some of these I think are like atomic elements, like tech or YouTube, maybe like covariance or something. Even though these are capital, they are not likely to begin a sentence and therefore are actually decreased. And so this makes sense.
This is particularly interesting because naively, you might just think, oh, the neuron's just going to boost the stuff that's likely to come next. The fact that it suppresses the stuff that's like actively not likely to come next is kind of interesting. And it's like maybe there's some separate circuit that boosts all capital letters because there's just like begins with a capital letter feature. And this neuron is needed to disambiguate the two or something like that. I don't know. I'd love someone to just go and like train a probe on the embeddings to look for features like this.
And then see how much they compose with these neurons. And yeah. Right. And then so just to round this out, there's also, okay, well, what are all these lowercase tokens which are being whose logits are being boosted, right? Like, if it's actually ending a sentence, like, yeah, this maybe doesn't make sense. But what we see is that they are indeed sort of many tokens which just like follow a period. So like WordPress, right? Like this is part of a URL. You would often see many things just like .wordpress or .amazon. Or would be implicated in codes like a .yaml file or something. And so this again sort of shows you that, well, okay, so maybe these neurons are doing a little bit of double duty and that they're also just reacting to the presence of a period rather than purely the end of the sentence. And on a specific example, like I found that one of the, I think this point right here, so this is the actual end of sentence which like least excites this neuron. It was a sentence which ended with the acronym LLC. So, it had periods that were sort of normally not in a end of sentence context, but actually did end the sentence. And so again, this is kind of like an exception, which proves the rule that it like tried to do the right thing in not activating for a non-sentence ending period, but actually it wasn't smart enough. And yeah.
A little neuron that tried.
A little neuron that tried, exactly.
And yeah, I guess this is just kind of a nice illustration of how probing can lie to you.
Yes, definitely.
I'm guessing you just didn't have URLs in the dataset substantially.
Correct. Or relative to other possible features, it was rare.
And presumably the lowercase words here do not begin with spaces.
Yes. Yeah. And I think that, yeah, probably a lot of the URL stuff is like what is on the right tails of like these actual end of sentence activations, which are false. Yes. Which, yeah.
Makes sense. Yeah, just for people who have not spent a while staring at tokenizers, the way the end of a sentence will be tokenized is you've got some word like mat, and then you've got a full stop, and you've got like a the plus the space is a token, the full stop is a token, and mat plus the preceding space is a token. So this is like, this happens, it's preceded by natural language. What comes next is the task being done here.
Precisely. So yeah, maybe just to round out some of these like additional analyses which you can do. So like in general, when you're doing when you're doing anything with supervised ML, when you're doing classification, you can sort of decompose accuracy into two metrics: precision and recall. So precision is, of the features which you claim are within the positive class. Let's assume we're doing binary classification. Of the features which, or of the data which you claim is in the positive class, what fraction of those are truly positive? So this is true positives over true positives plus false positives. And so this gives you a sense of like, well, so if you have low precision, sorry, let me also define recall. Recall is sort of the inverse of this. So this is like, of all the positive examples, how many of them did you actually classify were indeed positive? And so this is true positives over true positives plus false negatives, right? Things which you should have classified as positive but didn't. And so these two different metrics give you a foothold in sort of understanding the types of errors which your classifier makes, and therefore sort of maybe what the, if you're doing sparse probing, what these neurons are actually sort of reacting to.
Just trying to summarize the two metrics. Recall is like, this was positive. Did I realize it was positive? Precision is, if I say it is positive, I am right, goddammit. Even if I don't say it for like 90% of the right things, I will only fire when I am sure to hit the target.
Yeah, super positive that you're correct. Right. So this, can give you a little bit of insight into what's going wrong with, your classifier or the different neurons and how they're reacting. And so as a concrete example here, we have one neuron which we identified in Pythia 7 and 6.9b that reacted, that was low precision and high recall with respect to identifying passive verbs. So what this means is that it activates for almost every instantiation of a passive verb, but also activates for other things, in particular past participles and various types of dependency roles. The whole, this is a more grammar than you need to know, but essentially the point is just that it activates on things which aren't just passive verbs, but are like kind of related to passive verbs, like adpositions which are next to a passive verb, but they don't fire on any other types of verbs or really any other types of parts of speech. In contrast, the neuron on the right here is kind of the inverse, in the sense that it's a low recall but high precision verb neuron. So anytime this neuron activates, it's definitely going to be on a verb, but it might not activate on all verbs. And so in particular, it's, it especially likes infinitive verbs, but not like passive verbs. So in some sense, these neurons between them cover the whole sort of space of verbs, but they cut it up. I'm not a linguist, so it's not clear to me like why it makes sense to like think about infinitive verbs quite distinctly from passive verbs or past participles or those plural verbs which are in a root dependency role, right? And I think this sort of more broadly just shows again the danger of forcing your own ontology onto the networks, right? I mean, maybe a linguist can, explain to us why it's natural to have a verb neuron, but especially infinitive verbs, but not really plural root verbs or past participles or passive or adjective modifiers. Why this is like maybe a natural feature to represent. Neil, do you want to say anything here?
I think I broadly vibe with everything. I think this further illustrates my general point of all summary statistics ever lie to you. It is nice to have a bunch more summary statistics, but you ultimately really need to get your hand dirty and play around with your data.
Yeah. And I should also say that it's like rare that you can do like this fine grain of analysis. So this was only because, I was using some Penn tree bank data, which is like a popular data source, for all this data. But like normally you're not going to get this like very fine grained annotations on the types of features that are going on. So it was only because I had a richly annotated source that I was able to do like this really fine grained breakdowns of like different types of features. And so, this is like rare that you can actually do this, as fine grained. And so figure D, these plots are the exact same. The only difference is the scaling on the y-axis. And so these are the same neurons, and what they're showing are the activations of this particular neuron in archive documents when the token is part of the title of the corresponding paper versus not. And so, when you probe for this, assuming that you have like vaguely balanced classes of positive and negative examples, like your classes will like look vaguely balanced, and you'll train a classifier and you'll get like almost perfect accuracy, right? And life is good. The problem is this neuron also activates for these other rare features. This again sort of shows the importance of having good negatives, because if your negatives are only sort of sampled from this hump of the distribution, and which is, because this is a log scale, this is the vast majority of all possible tokens, you'll get a really nice classifier and you'll be like, yes, this is a monosemantic neuron, life is good. Yeah, whereas if instead you sampled things from sort of this part of the orange distribution, you would be like, wow, I have a really shitty classifier. And so this again sort of illustrates the dangers of data-specific interpretability methods. I will say this story has kind of a happy ending, because it turns out, it seems like mostly what's in this right tail of activations for this neuron are section headings, which feel like morally like they're titles. And so again, this is kind of an example of where the exception proves the rule, that like, yes, that like this neuron is activating for sort of, headings in general of archive documents, of which titles are an obvious subset.
Nice. I was about to say, like, those are two ridiculously well-matched mounds. I'm sure the orange thing is a everything else plus some other feature. Glad to know that the prediction I did not pre-register and could have just come up with on the fly was correct.
Yeah. Yes. Now, I didn't, this again, it's hard to do rigorous investigations for every single neuron, but just looking at dataset examples, this seemed to be a very strong pattern, and it really didn't seem to be activating on much else besides section headings.
Do you have any other illusions that came up that weren't in the paper, that weren't in this figure?
I mean, one fun one that we already sort of showed was the Canada neuron one. Yeah, I think a lot of the LaTeX features actually seem to like be doing double duty in various kinds of ways, but none were quite as clean as is title and is subtitle addition.
Yeah, I feel like I did not appreciate this figure when I was helping review and write the paper. Such a good figure.
D in particular?
I really like D. I kind of just like the whole. Wait, no,
Yeah.
I like D so much. D is like, I look at it and I learn a lesson.
Yeah.
Otherwise, I'm like, well, I stare at the thing, I stare at the legend, and I'm like, I can kind of figure it out. But yes, it also makes me sad that the color schemes of the two plots in B are the same, because they're different things. And so it looks like two identical plots until you look closely.
Yeah, I mean, the
Anyway.
y-axes are different and the legends are different and the scales are quite different.
It's so small. Anyway, I'll stop complaining. Yeah. I have extremely strong takes on optimal plot, as Wes has learned. All right, changing tack a bit. I think one interesting thing to dwell on is motifs in models. Generally, models have lots of internal structure and patterns, but not that much effort has been spent kind of being biologists inside language models, going out, seeing what we can find, having the potential to be surprised. And one thing which we found here that I think is particularly interesting is this motif of disambiguation, where by motif, I kind of mean like a general high-level pattern and structure that you can notice and identify and like predict you will see in other contexts in a kind of fuzzy, not incredibly crisp sense, but in a way where this can be part of your intuitions. And I feel like a good chunk of my growth as a researcher has just been like getting enough context on models and having enough random experiments and reading papers that I have an intuition of like, oh, this kind of motif could come, or this kind of motif could come up, etc. So the motif of disambiguation is that there are often features that like mean a small handful of specific things. For example, const means a different thing in a small handful of programming languages. each language, like Go or I don't know, Java or C, is like a clear, coherent meaning, but the const feature just tells you it's one of the four. And this is much, much less useful. And the goal of disambiguation circuitry is to take something like that and disentangle it into these four separate features. And in large models, what you'll tend to get is something like a const in Go, const in C, etc. But here, the model seems to be using this more efficient compression scheme of instead having an is-go neuron, and then is-go plus is-const becomes the go const in Go feature, etc. And this is like less good, and it's less linear, it's less cleanly separated from everything else. But if you have sufficiently strong I am Go, I am C, I am Java features, then this should give you useful I am Go, I am constant Go features. The trend where small models have individual neurons, small models have like a neuron for Go, large models have neurons for many different things, is another motif called neuron splitting, where you start with like one big feature, which is really the union of many tiny features that would be somewhat useful to disambiguate, and the bigger you get, the more you get split. Do you want to explain this graph, Wes?
Yeah. So maybe just like a concrete example of neuron splitting would be like an all caps feature, where there are like many reasons why an individual token could be in all capitals, right? It could be like a Python constant. It could be, some random internet text, someone screaming. There are many reasons why you might expect all capitals, but the sort of underlying semantics of a Python constant versus someone screaming on the internet are like quite different, and therefore the text which is likely to follow would be quite different. And so like disambiguating which of these cases is actually correct might be useful. And so in this plot, I guess maybe we can start with B. It shows for each of the different model scales. So this is the x-axis for different features. These are the different lines. We look at the classification performance of the best individual neuron. And so essentially the best one sparse probe. You can see that for certain types of features, so like whether or not a particular token is in Python, or whether or not a person plays football, there's like this strong emergence that happens. And so as the models get bigger, there are neurons which are like more and more on their own can be used to like classify these different features. There are other types of features which are just like so important for a language model to do, right? So like, a language model needs to know whether or not it's ending a sentence, or like the basic part of speech facts and whatnot. And so even in the smallest models, these features are represented consistently, and maybe not with 1.0 accuracy, just because the data set's like a little bit weird or something, or it's maybe it reacts to other things, etc. Then again,
that I think this is a slightly spurious distinction because it depends a lot on which model sizes you're looking at. Like if we looked at is Python from 1B onwards, we might call it a constant feature. It's like a matter of perspective.
Yeah, in general, what I imagine is that, there are a few different regimes. So if you imagine like, sort of infinite model size on the x-axis, and the sparsity of the representation, or maybe, the sparsity of representation on the y-axis, you can imagine initially for like a tiny model, basically nothing is represented. And so it's like maybe just like this mess of correlations, and that's like the best you can do. And so everything is like fairly dense. But then as you add more capacity, your features get sparser because you can represent them in superposition and have less interference between features as you increase model size. And then for models which are big enough, and for features which are important enough, it makes sense to have a dedicated representation, a single neuron for a particular feature. So in this case, that phase transition might happen at like 1 billion parameters for Python. However, as we were discussing, eventually you might want to disambiguate even further. So this is kind of like how in native Alaskan languages there are like 8 different words for snow. So in this case, there's additional returns to sort of being more specific. And as you increase your model size, you have more capacity to have this finer grained resolution. And therefore, these monosemantic features might get split. And therefore, from the view of sparse probing, the sort of overall feature of snow is now the union of all of these like 8 different types of snow. And so maybe, there's a neuron for each of these different types, and you need an 8 sparse classifier to recover the snow feature, where it's just like the sum of all of these. And so the split features, and then there's other features which are just like a little bit more random. They don't seem to have a super clear pattern. I think that, yeah, there are various other confounding factors with the data set, and these are maybe just like correlates of something, and it's just so like, how are some of these correlates represented and whatnot. Yeah. Do you have anything to add?
No, I broadly vibe with all of that. Obviously, all of this is messed up by we don't have that many data points. Different models are going to have a lot of noise. The Pythia suite now has like 4 models of each size, which is kind of nice. And plausibly, if we can be bothered, we would rerun all of these for different models that, Wes probably can't. At least for the 7B, which I presume is like more of a pain than the rest put together.
No, the 12B is more of a pain than the rest put together, which is why they're not shown.
I was just saying the 12B doesn't even exist, man. It's a fake model.
Yeah.
It's not real. Okay, so I guess changing tack a bit, what can this tell us about how model change as they scale beyond these observations on Neuroscope?
A paper which I really like is the quantization model of scaling by Eric Michaud and Max Tegmark's group, which sort of hypothesized that there were like these discrete atomic features that are useful for language models to represent, and that there's kind of a natural ordering of these features. So like part of speech is just like, something that any halfway decent language model, just like basic grammar, it's definitely got to know. And so these are like early within this like feature ordering of like very important features to learn. And that as you add capacity, you can sort of like learn more and more of these features. But because these features because natural language in general has like a lot of power laws in them, this sort of explains the power law scaling observed within large language models, because these features like have power law returns to representing them.
And Eric had some very cool results showing that if you make certain assumptions about the distribution of these underlying quanta, which I think of more as circuits than features, but I guess it's kind of equivalent.
Right. Yeah.
Well, where feature is like a property of the input represented in activations, circuit is an algorithm used to compute features represented in the weights, but it's all kind of equivalent because circuits give you more features. Right. Yeah, he showed that if you make certain assumptions about the distribution, you can recover smooth scaling laws, though it was mostly a theory and position paper rather than this actually happens in real models paper. But we have some evidence.
Right. And yeah, so you can also sort of think about like what happens as you vary the sparsity of the probe. So like these are essentially all like, figure 4B here is essentially all one sparse probes. But you can imagine like, well, maybe, maybe a small model like has really bad one sparse representations, but it'll have like really good K sparse representations. What we mainly see is just a sort of a difference in the consistency across different models. So for example, in the part of speech, what I glean from this plot is that all models represent part of speech with like approximately the same sparsity. And so that actually like there is no returns to scale, right? The performance, the performance of one sparse probes are like all comparable. The performance of 10 sparse probes are also all comparable. And so like, all model sizes are representing part of speech, and like maybe not in the exact same way, but at least with the same amount of sparsity.
Just to clarify what this graph means. So I believe what you've done is you've taken the 10 parts of speech we're probing for, trained probes of each sparsity for each of those 10 things, and then just taken the mean F1 score. Is mean even principled here? I've gone for median.
So yeah, I think I checked and it's pretty close.
Great. So this is like average over a lot of stuff. So it's like less surprising that it looks incredibly smooth than it might seem at first glance. We're just like, the fuck. I'm still low-key like, the fuck. But
Right. Yeah. And so, in contrast, you get something very different for factual features. And, this makes sense because, again, like knowing basic grammar seems super important for even a tiny language model. And so this is going to be represented. In contrast, knowing that like some, super random soccer player is a soccer player, it feels much less important. It's much less loss reducing. And therefore, you would only expect to have this with any sort of compact representation in large models. Yeah. Also with factual features, you get sort of less returns. Like it helps less if you use more neurons in your classifier. I think this makes sense mainly because in part of speech, there are probably many possible correlates. So there's sort of lots of subtle linguistic cues where the certain activation pattern would only happen in the context of like a verb or something. And so you can use, I imagine that a lot of this return to scale is like more correlational than actually having like superposition across many neurons. Yeah. Whereas in contrast, is someone a baseball player is going to have like far fewer correlates. It may be correlated with like just things about baseball, but there are like many fewer linguistic cues that you're likely to pick up on, and therefore the returns to sparsity are less. And so these curves are a bit flatter than here, and likewise for plain text features.
So part of speech is like verb, noun, adjective, adverb, etc. And the text is just labeled with those, and you probe for those. What are plain text features?
Right. So plain text features are like kind of a bunch of semi-random things. So I think this is like, does the token contain a digit or not? Or like, is this token not ASCII? Or, is this token all caps? Or just like things which like are regexable on the value of a single token.
All right. Programming languages we've already discussed.
Yeah.
And factual
And then,
features are like, what? You have some attributes like soccer player, and you
yes.
look at a bunch of soccer players and a bunch of other athletes, and you check for neurons that only
Right.
activate for the soccer playing ones.
Yes, that sort of classify soccer players from non-soccer players.
And this is importantly not obviously necessary for pure factual recall of like outputting Wayne Rooney plays soccer or something. Well, Wayne Rooney plays
Right.
football.
This is rather reacting to a pre-computed soccer feature, most likely.
Yes. Like there's probably detokenizations that figure out
Yes.
that Wayne Rooney was there that output the I'm a football player feature, and then later neurons that like for whatever reason aggregate these I'm a football player features.
Correct. Yeah. And in fact, most of the sort of most prominent athlete neurons that we found were clustered into later layers.
In a massive model.
Yeah, in a massive model. Yeah, this is 32 layers. And I think at this point, it's actually worth mentioning a few other sort of subtleties with when you're doing sparse probing, is that there are sort of multiple reasons why you could have a sparse or there are multiple ways in which you could have a sparse representation of a feature. So imagine the feature is a live female soccer player. This is like, in some sense, a composition of three features. If you have a sparse probe, which is like really bad for one sparse, but is really good for three sparse, based on earlier discussion, you might be tempted to be like, superposition, yes. A perfectly other reasonable hypothesis, one which I think is actually probably more likely for this specific example, is that you have neurons for is alive, is female, and is soccer player. And that the sum of these, or the composition of these, is actually sort of what is representing the is alive female soccer player. But again, from the sort of point of view of a sparse probing experiment, your three sparse probes would perform well in either case. And it's only with the secondary analysis of being like, oh, well, okay, this one is obviously a soccer neuron, and this one is obviously has to do with whether people are dead or alive or not. And again, we sort of just to drive home the point, in Pythia 6.9b, there seems to be neurons in most layers which are like that separate pretty well gender, or like whether or not a person is alive or not.
Where gender is whatever Wikidata says that we have expressed zero opinion on.
Yes, exactly. um, and so this also sort of gets at the point that in our current probing setup, we've only been looking at things from within a single layer, but models likely have composition or superposition even across layers. And so in our current probing setup, we're not looking at that. You could maybe concatenate all the activation vectors together and then run probing on that. But this becomes super high dimensional, and will get a little bit messier.
I would love to see someone do that, to be clear. Seems
Yeah.
super interesting to me.
If you were to do that, you should do maximum mean difference rather than any of the other type of feature selection methods, because otherwise they will probably be too slow.
Do you want to briefly discuss feature selection method?
Right. Yeah. So, okay. Yeah. So one thing which we've been awkwardly ignoring, hold on, let me pull up the right.
Or maybe one final thing is just
Yeah.
clarifying the superposition across layers idea. So conventional intuition about networks, you have layers. The output of each layer is the input to the next layer. And the thing at layer K is like the thing at layer K. Layer K owns it. This is just not remotely how models with a residual stream work, especially not transformers. Instead, you should think of residual stream models as ensembles of shallow paths. You've got like 20 layers, which each read and write the thing, but each layer on its own is like, yeah, you've got like residual stream, you got a bunch of stuff that reads and writes to it, but any given thing is like probably here, and then you clipped along here for a bit, and then it goes out here, and then it's up here again. And, you know, in the 20 layers, it'll go through like maybe 3 or 4 of the blocks. And lots of these are happening that intersect at different levels. And for some reason, this makes the model happier than having like more residual stream bandwidth. Also, I try to be very careful to always drawing models with the residual stream down the middle and layers to the sides, because people often draw it the other way around, and this is incredibly misleading, because then the skip connections seem like a cute bonus thing rather than the entire point. And it's very annoying. People do not get models. Ugh. So this means that if you've got a circuit, which is like here, here, if the model wants to use 5 neurons in this layer, it doesn't really care whether they're in this layer or there's some in this layer too. From the perspective of superposition, especially in bigger models, there's just like no good reason why things need to be restricted to a specific model.
Specific layer.
Yeah, specific layer. It's very hard to have superposition across models. Believe me, I've tried. And yeah, slid across layers. And there's like some messiness because obviously the next layer sees a somewhat different input. There's some composition happening. But because of the residual stream, plausibly the key inputs haven't changed that much. I would be very excited to see someone actually exhibit meaningful superposition across layers. One of the things which is hard about naive things like just concatenate the neurons and train over that is that you need to distinguish between where the model computes a feature and where it uses the feature to do other stuff. Because, yeah, you can detect social security, and then you can use it for, say, a welfare neuron. And these are two fairly different things in terms of how they're used, but in terms of correlations, they look exactly the same. And the later in layers you are, the more you need to care about stuff.
I think the athlete neuron example is also a good example of this, where like, and we actually tried to causally ablate these neurons and trying to, make the model think that a soccer player was actually a baseball player. And it seemed not to work with those like later layer neurons. And I think that this is an example of the model not using that feature, but rather than computing the feature, it's only using it for some other thing, which isn't implicated in whether or not the person is actually a football player or not.
Cool. All right. Shall we return to methodological things people should know about sparse probing?
Yeah, there's kind of an elephant in the room. We've been talking about all this sparse probing stuff and being like, oh yeah, only use K of the neurons out of like the D neurons within a layer. But if you know a little bit of optimization, you're like, oh hey, wait a minute, they're like, you choose K possible such neuron subsets, this is a combinatorial problem. How on earth are you like choosing which K to select?
Some fun subtext to this paper is that Wes is a discrete optimization PhD student.
Right.
And originally, he wanted this to be a exciting optimal methods for doing machine learning probing paper. And I have very gradually worn him down, making this a superposition paper. Though I did not quite get him to put this in the title. Though I did get Finding Neurons in a Haystack in the title, which remains the best title I have ever come up with, as you were.
Yeah, so indeed, most of the stuff about feature selection methods and the results got relegated to the appendix. This is definitely primarily a interp paper rather than a methods paper. And we also, it ended up the methods being like largely similar. But anyway, so yeah, how do you actually select the K neurons out of this set of D? And so there are like a few different heuristics where, usually how this is formalized is like ranking or scoring. So you have these D neurons and you assign each one of them a score. And then to train the K-sparse classifier, you just take the K neurons with the highest score. And so a few such like scoring rules or functions, the easiest one is just the mean difference. So you have a bunch of activations of a neuron when it's on a verb versus not a verb. And you literally just take the difference in these average activations. And so for a verb neuron, which only activates on verbs, then this mean difference will be very large. Whereas if, the activation of a neuron is like pretty uncorrelated with whether or not the current token is a verb, this will have a small mean difference. Yeah. So this is just like one very, very cheap to compute ranking function. And it turns out to work basically just as well as the fancier stuff. Yeah, you can also do mutual information. That one works the least, so I'm not going to talk about it. F statistic, which is kind of similar to mean difference, except you're looking at the variances rather than means. So it's like the second moment rather than the first moment. I think a lot of people's initial reaction is, lasso, let's do L1 regularized logistic regression. This is like, again, decent as a heuristic, but it's well known that L1 methods actually aren't that great for feature selection, especially in the presence of like correlated data. And so this is like I would expect especially to be true within the neuron activations on like a data subset of interest.
You say it is well known. I do not know this. Please explain.
Okay, so there are like all these. Okay, so there are a bunch of like very famous papers in the mid 2000s by Terence Tao, among others. It's if you look at Terence Tao's most cited papers, they're all like various L1 perfect recovery results. But they like rely on these like specific properties. I think the restricted isometry property RIP is the famous one. And I forget all the conditions, but like it essentially breaks down in the presence of correlations within your data. And like most data is like going to be correlated, right? Most natural data. And so like this, and I would expect it here. And therefore for, naive L1 things to like not work quite as well. Although, as I said in the results table, everything is like decent, is like reasonably similar. And so, right. And so the reason why I initially had the idea for this project is like my advisor is the author of this paper, which like figures out a more clever formulation for doing cardinality constrained prediction. So this is like, when you want a classifier or also a regressor, which uses at most K coefficients, how to actually do this optimal NP hard feature selection problem. The details are out of scope for this discussion, but it uses some, fancy cutting planes magic, although it doesn't actually scale that well. And so you need to do some heuristic filtering at the beginning anyway. And then the sort of last method, which is good for sort of sweeping different values of K rather than just super small K, is adaptive thresholding, where you train a classifier, let's say with K prime neurons. You then, or maybe even a dense probe, which is the D neurons. Sorry, you then sort the neurons by the absolute magnitude of the coefficient. So neurons with larger coefficient in the classifier, you assume to be more important. You then train a new classifier with D divided by 2 neurons, those which had the highest coefficient magnitude of the previous probe. And through this, you can do this like halving thing such that you need to train like log D probes where you successively sort of have or somehow decrease on some schedule the number of neurons being used. And this is like a really nice way of sort of sweeping over a large value of K of different neurons and like using sort of the intermediate results to sort of guide your search a little bit more. And so when you should use them, mean difference, if you want something quick and dirty or like at scale, mean difference is probably your best bet. If you want to sweep large values of K, doing this adaptive thresholding thing with like a small L1 regularization is probably your best bet. And if you like really want to prove optimality and like for some reason, like actually having provable statements that you couldn't do any better is like especially important to you, then the optimal sparse probing is a good idea. Though again, like, you know, it sometimes takes a long time. In this case, it timed out. Like we set a 60-second timeout, and like, yeah. So this is probably best in like toy models where you want to make theoretical statements. Is probably the sort of most useful case for OSP.
Makes sense. Is adaptive thresholding not on the table?
Adaptive thresholding is not on the table.
Sad. How did it do?
I know. So I always use adaptive thresholding for like very large values of K. And so I just didn't clip it and put it in. But this is something which conceivably I should do.
It's bad. It's a bit of a bad look, man. Mostly I'm curious about the runtimes.
Oh, I mean, it's, yeah. So it's like, well, so the runtimes are also like a little bit complicated because like for some of these, you only have to run it once, right? So you only take the mean difference once, right?
Yep.
Whereas for some of these, you have to actually retrain something for each K individually. So that would be like OSP or adaptive thresholding. But yeah.
Mm-hmm. Makes sense. But so max mean difference is selecting a set of K that you still then need to train a probe on, right?
Correct. But for K in this range, the cost of training a logistic regression is pretty trivial.
Makes sense. Oh, this is literally 1 to 8. You're not including like
no. This is a tiny table. This is a tiny table. Yeah. Yeah, and they all end up being approximately like these are not large differences, which is why this table is in the appendix.
All right, a couple more questions. So adaptive thresholding and L1 both have hyperparameters for the L1 and the L2 regularization.
Yeah.
Thoughts on what they should be?
The default scikit-learn hyperparameters are usually pretty good. I did do some tuning, but yeah, they ended up being approximately right just out of the box. So you can actually do better with adaptive thresholding by like the optimal regularization strategy kind of depends on what K is, because you know your K equals 256 probe, you're not just using for the sake of the 256 probe, you're also using it as a feature selection method. And so there is a small trade-off between like selecting your hyperparameters to make them amenable for feature selection rather than just quality of fit. And so like I did a few experiments and like found some schedule that like seemed to work well, but yeah, I mean it's not an earth-shattering difference.
How different? So you train a linear probe on all 3,000 neurons. You then train it, you do adaptive thresholding, you train it on 1,500. How different is the rankings given by the two?
I didn't look into this super carefully.
Fair enough. I mean, naively, I'm just like, well, surely it's about the same, right? I don't know, man.
Yeah, and so you can imagine being more aggressive with your schedule, right? Or like maybe like concretely what I did is like I only filtered for, because logistic regression is pretty expensive on the full, especially for large models on the full dimensionality. I think what I did was, no, I mean, in and of itself, doing it once is not that expensive, or it's like maybe a few minutes. But doing it for all of the layers, for all of the features, for all of the models gets like quite expensive, even if you're doing it in parallel, right? Yeah, and so concretely, I mean, most neurons are like totally useless, right? And so you can usually just like throw those out immediately with like mean difference or some other like really cheap heuristic. And then after you've already cut your space by, a factor of like 4 or something, then do a logistic adaptive thresholding with the logistic regression. Because you can imagine, a logistic regression scale is like O of n by d. And so if you cut d by a factor of 4 up front, everything else is like much cheaper than what training those initial probes would have been. So like if you're actually doing halving, the biggest probe which you train always accounts for like half of your compute time.
Yeah. What's the time complexity of training a logistic regression?
Order ND.
Thanks. Where n is number of data, n is
the number of data points,
and
D is
points.
Yeah.
Gotcha. Well, that's shockingly cheap.
Yeah, because I think it's just gradient descent on n by d. Over a d-dimensional vector, which is your coefficient vector, over the whole data distribution, which is factor n. So it would actually be like, times like the number of batches or whatever. Like, yeah, but I think we assume that it's like some constant number of batches or whatever. Concretely, we literally just give it to scikit-learn and have it deal with it.
Makes sense. Where batches here means epochs, right?
Right. Yeah. Epochs. Yeah. Sorry.
Gotcha. Interesting. How big are your data sets here?
We have a handy dandy table. The number of sequences, the context length, the number of non-padding tokens for each of the different probing data sets.
Oh wow, natural language.
Right. I'm realizing, do we have the table of yeah, okay. There potentially needs to be another column here of like how many things are actually in the like data set. So like for the sequence features, like each one of these corresponds to a different data point, right? Because it's at a sequence level. Whereas like for part of speech, basically every token has a annotation associated with it. Although we typically use a subset on the order of like 20,000 or something. Yeah.
So when you train your probe, you've got, say, 20% positive. Do you do anything to like balance this better?
Yeah.
Like you take a quarter of the negative example, so it's 50-50 or what?
Sometimes it just works out that like a feature is kind of naturally balanced. But in general, with all of our probes, we do include class weights such that they're sort of balanced in terms of importance. So that, within the loss function, getting each data point classified correctly is not of equal weight. The positive classes have higher weight, that they're more important to classify correctly. And this is because usually the negative set is larger than the positive set. And so we don't want the case to be of just like have the classifier just like say everything is negative, because that would get like 90% accuracy or something. We have balanced class weights. And you can, this also intersects a little bit with the sort of with the precision recall balance of like any classifier. Depending on the class weights, a classifier would maybe prefer, or it would be loss reducing to trade off precision for recall. And these are exactly in tension with each other.
Gotcha. And concretely, what we have here is like, so when you say class weights, do you mean you take a quarter of the negative examples at random and train on that? Or do you mean you multiply loss by a factor of 4 for the positive ones? Okay, cool. This makes sense. Any other methodological things people should know if they want to use these techniques?
Yeah, so I think dataset design is the big one. There's just like pretty hard to get right if your feature is like especially narrow or subtle or something. Just like designing like the right set of negatives to really just like separate out just exactly what you want from all possible correlates, I think is quite difficult to do for like non-trivial features. Yeah, I think sparse probing, like literally just like sparse probing itself, I think is much easier to get right. Again, maximum mean difference, basically good enough for like most things. And just, sweep for different values of K. And, this curve tells you some things about like how sparsely represented something is. I will say one other maybe methodological note is that let's say there's like a neuron which is like really good at detecting, French or something. If there are like naively sparse probing will not, if you have K equals 1, will just give you one neuron, but there might be multiple neurons in a layer that are really good at classifying some particular feature. And so depending on the purpose of your research, like if you want to be exhaustive, you might need to do like the second stage step where you're like, okay, I found this one neuron, which is really good. Let me just like consider all other neurons, which are not this neuron, and see how good that is. And I think, yeah. And so we did have some results on this. This is kind of like actually, where'd it go? These plots where we have neuron rank. So this is like a different neuron for each, or like these are all individual neurons. And you can see that there are like many neurons which like individually are pretty good at classifying social security from X security and social Y. And yeah, we call this iterative pruning. So this is maybe something else to be aware of.
It is kind of striking just how many there are. I guess I don't know how to interpret F1 score.
Yeah, F1 score you can think of as like a balance of precision and recall. Yeah, I mean, yeah, perfect F1 score would obviously just be a perfect classifier. And then there are like two ways that F1 score can go down, either poor recall or poor precision. And I think for n-gram neurons, it's almost always poor precision because they're polysemantic, there are like many things which also cause these neurons to activate, but they do reliably always activate on the bigram of interest. So like they always activate on social security, but there's like maybe lots of other random stuff that also cause the neurons to activate.
Yeah, maybe rephrasing the question. I don't know what it means to have an F1 score of 0.9 versus
Right.
0.8. Do you have intuition for how to interpret the numbers? Like, reverse engineer them.
Right. So like I said, there are sort of two reasons why you could like this is I try to give an answer in the sense that like there are two ways in which, or I guess three ways in which this metric could be like bad or different. And that's, because the model has some number of false positives but like no false negatives, or it has some number of false negatives but no false positives, or a few of both. And so there's actually like many things, there's like a whole curve of things that 0.9 could mean in term an F1 score of 0.9 could mean, depending on this balance of precision and recall. A 0.9 F1 score would be consistent with a classifier which was 90% correct on both claiming things were positive when they were in fact positive, and also identifying 90% of the positive things.
Any final thoughts on these topics before I move on to the next section?
I don't think so, no.
Cool. All right. So MLPs are 2/3 of the parameters of a transformer. For the most part, most mech-interp effort has been focused on attention. What are MLPs good for? What do MLPs do? And what kind of things should we expect them to do? Conveniently, we do have an FAQ question on this somewhere. A14. Yeah, sure. How could we forget the right number?
The Solu paper, I think, gives a few good intuitions for what could be going on. A few motifs here are, in early layers, you have detokenization neurons. So these are neurons which, again, go from like raw token space of having HARs and VARDs to Harvard, the like, university, which has all of these distinct properties that you probably wouldn't want to fit into the HAR and VARD token independently. So these are, detokenization neurons, which happen primarily in the early layers. Another sort of motif are more conceptual neurons. So these like might be context neurons, which react to like a higher level property of the input. These seem to be more common in the middle layers. And then finally, ultimately a large language model needs to make a prediction for what the next token is. But in these middle layers, potentially operating in this higher level conceptual or semantic space. And so the model needs some circuitry to sort of convert this conceptual or semantic space back into the token vocabulary. And so Anthropic calls these retokenization neurons, which go from, semantic space to actually what is the next token. Another mental model for thinking about what MLPs are doing comes from a line of work by Jiva et al. And this is, there's one paper in particular which posits that MLPs sort of operate as key value stores. And this is importantly distinct from keys and values of attention heads. This is more in sort of like old school Like you could even think of it as like databases, right? That you're given some key and you get some value whenever you give a certain key. And here again, like within the key value framework, a whole layer of neurons are reacting to specific types of keys. You could think about these as maybe features or some subset of features which are present. And whenever the specific key is present, the MLP layer collectively gives some value. And this value is a update to the overall output distribution of next possible tokens. And so, yeah, the authors do some things where they decompose the layers into, they show that there's like some additive update structure, which is kind of interpretable. And so you can see different neurons sort of boosting different distributions.
Well, that's part of what the neurons do. I don't think they showed it's all of what the neurons do.
Sure. Yeah, of course. Yeah.
But yeah, I find the key value store thing interesting because it's like a very compelling, naive hypothesis of what's going on. Like neurons fire if they have a certain input and they produce a certain output. Obviously, this is a lookup table, at least if you're not thinking about superposition. But it's like actually much more subtle than that. One of the things that's kind of weird about neurons is that the input is a 1D projection. It's just like, take a direction, and it's saying, if this crosses a certain threshold, then output this other direction. But this means that what you output was, by definition, already represented, assuming that you can basically treat the GELU like a ReLU, which I'm just going to go with for now, even though it might not actually be true. And this means that the thing you output already was linearly represented. And so basically the only way MLPs can matter is if they're doing some kind of sharpening or some nonlinear transformation. Like this is in some sense what detokenization neurons do. Like if you've got social security, there's a social direction, there's a security direction. Some of the two is already an okay detector. The MLPs sharpen it to a much better detector. And similarly, if you have a key like Eiffel plus tower, then the value of in Paris, you could just also have whichever bit created Eiffel also created a bit of in Paris, whichever bit made tower also created a bit of in Paris, so that the sum automatically contains some is in Paris. This is like less of a good idea because it's noisier. You want the MLP to sharpen. But this means that you should only expect key value stores to matter when they are doing some sharpening. And in particular, I think this means that you can think of key value stores as basically just a glorified AND gate, where if you have the two keys of Eiffel and tower, the key is like the sum of both. This makes total sense. While if you've already detokenized Eiffel Tower, it's like much less clear that you even need a key value store at all. Because when you produce Eiffel Tower, you could also have produced an is in Paris. Plausibly, a neuron could also be doing some kind of OR gate. Like if there's 20 different landmarks that all occur in Paris, they're never going to occur at the same time. You could imagine a neuron that activates for any of them that produces a nice, clear is in Paris direction that like maybe is easier than each detokenized thing doing it. But I think it's kind of subtle. And one important implication of this is that detokenization neurons can simultaneously serve as key value stores. In some sense, they are a key value store. The keys are the constituent tokens. The value is this token is here. But you could also take anything else you want to be looked up by the Eiffel Tower detector, like an is in Paris, and output that as well. And in particular, I conjecture that detokenization neurons are where the model stores factual knowledge, rather than needing separate circuitry for this. And no, neurons, they're really subtle and weird.
Yeah, and I think that, this was showed tentatively, I think, in a recent Jiva paper, and, was also implied by maybe the original Rome paper, that the sort of early MLP layers were implicated, although there have also been subsequent papers from, I think, Peter Haas that showed that, this is maybe a little bit subtle.
Well, I think specifically the thing that happened there is people did causal interventions that showed that early MLPs seem to matter. Right. The Rome paper then optimized an addition to the model to try to edit in a fact, I think there was maybe some implicit claim that doing this editing helped you localize where the fact was, but inserting in a fact is not the same as editing it, because it's much easier to insert in a loud fact that drowns out the old one. The editing specifically didn't really tell you where the fact was stored, and there was subsequent work like Haas et al. There's also a paper at the ACL conference showing that if you had prompts like, if you edit it to think the Louvre is in Rome, and you give it a prompt like, I love the Louvre, Barack Obama was born in, it also says Rome. But then there's the separate half of the paper that's about causal interventions, which is also what Morgaver's follow-up looks at. And that also finds that early MLPs matter. I'm specifically making a non-trivial, stronger claim that not only do early MLPs matter, it is the same bits of the MLPs that are doing detokenization, rather than say, detokenization happens and then there's a separate is in Paris lookup. In particular, I'm predicting that the is in Paris detokenization outputs everything the model knows about Paris, because at this point, it doesn't know what relationships it wants.
Yeah, and then the last thing I would just say is that I think the key value store, if you want to be reductionist, like, okay, yes, it has an input and it has an output. We have keys and we have values, like, sure.
Only if it's a monosemantic ReLU.
Well, but I mean, even if it was just literally, matrix
sure.
multiplication,
like
you could just be like, oh, input, output, keys and values, sure. But I think that there's maybe some useful factorization into actual keys and actual values that makes this more interesting.
Yeah, another thing which is kind of non-obvious for people starting out in MechInterp is that models need to do all kind of management and maintenance of their internal activations. For example, they have a previous token head that outputs a bunch of information to a subspace. But then as layers go on, the residual stream norm increases, which means that as a fraction of the available information, that subspace gets smaller and eventually kind of gets essentially overwritten, because layer norm scales everything to always be unit norm. This means that models are incentivized to identify the bits in there that are important and signal boost those. It's plausible to me that the way you want to signal boost those is by having neurons that detect and boost those, which is just in some sense, looks like a key value store where the key and the value are the same thing. It could also decide to overwrite information that has been there that's no longer needed, which is like a key value store with negative. I believe you could detect both of these automatically by looking at the cosine sim of input and output weights. This also might be a counterpoint to my detokenization is also factual recall hypothesis. If detokenization is in layer 1, the MLPs for moving facts around are in layer 17, maybe the model wants to only recall the fact in layer 14, because otherwise it'll just be lost or consumes bandwidth unnecessarily in between. Generally, the way I think about models is that the residual stream bandwidth is a really precious, scarce resource. Parameters are fairly cheap, and neurons are cheaper than residual stream elements. And so it is sometimes worth the model spending some parameters on cleaning up what's going on. The final thing that's interesting to chat about is this idea of retokenization. In some sense, the story of this paper is we've understood 2/3 of the model. We have early layers, which are mostly doing detokenization. We have not rigorously shown it's most of what they're doing, but I'm YOLO. It's a lot of what's going on. We've got middle layers that seem to be doing conceptual reasoning, where is this French is one such example. And then the natural question is, what are late layers doing? Wes, do you want to explain this and explain your valiant efforts to solve this and failing?
Yeah, so right. So we tried looking for these sort of types of retokenization features. And, in particular, when we were always probing with respect to a feature of the current token. So is the current token a verb or not? But you can imagine for any competent language model, it probably knows that the next token should be a verb. And so you could literally just shift your indices on all of your data sets by 1 and be like, okay, I now want to train a probe that predicts whether or not the next token is a verb or not. And this would give you some information about what are neurons which are especially implicated in the output. we definitely found neurons which were like decent at this, but nothing which was nearly as clean as like a lot of the other results that we got. And so we kind of reviewed this as a negative result. One reason why I expect that this didn't work is that we did the really easy thing of just predicting the property of the actual next token rather than what the model predicted the next token to be. And this is large part just because like we didn't have the supervision in the sense that like we did know what the actual next word was a verb, but depending on it would be like a lot messier to decide whether or not the output of the model was a verb or not. Depending on like different tokens have different parts of speech potentially, and so it would be a bit ambiguous. But anyway, I think that this is the right way of doing it. Would be to train a probe on what the model actually predicted, and I think that you probably could get better results if you do that, but we did not, and so therefore our next token probe seemed to be substantially worse than our current token probes.
Okay, so first off, a problematic thing about thinking about retokenization is that, so the model thinks there's Eiffel Tower has 4 tokens. The model outputs the E without needing retokenization at all. But then if the model outputs if, it could be because it has the is Eiffel Tower feature on the like token before E, and it uses that with some retokenization circuitry to see that it should be if. Or it could be an n-gram continuation circuit, which says E was the previous token, so if is likely to come next, because there's a common bigram, because Eiffel comes up a bunch. And like it's hard to tell the difference. If I was trying to plan out a project on this, I'd probably be like, okay, let's look for neurons that activate on specific tokens and n-grams, and where the neuron's activation is correlated with the log prob the model put on the first token in the n-gram as a metric for like the model knew what it was getting into.
Right.
I don't know if that sounds like a coherent project, Wes.
I think that's a reasonable thing to try. I'm not sure that this cleanly separates the retokenization from other types of like recognition of like this is the Eiffel Tower.
How so?
Well, so if a neuron is a retokenization neuron, I think it can still be a retokenization neuron without activating on the token before E.
Sorry. I think I misphrased. So my prediction is that retokenization neurons hard code what the next token should be. Like it will just boost L. And so it can't activate on the token before E, because that would be bad.
Oh, I see. So it's explicitly not on that.
No, what I was saying was, so the two things that you do to identify a retokenization neuron, you'd look for weights that boosts L, and you'd probe things that activate on the if in Eiffel Tower, and you'd look in late layers. But this doesn't distinguish between an n-gram detecting and continuing neuron. In late layers, because it's about continuing the n-gram, not just about detecting it, and something that's composing with the fact that the model knew Eiffel Tower was coming, and it converted knowing the Eiffel Tower was coming into E, if, L, Tower. Plausibly, the model just doesn't even need to do this once it gets good enough that an n-gram continuation neuron can take over, and that this is just kind of boring. But my guess is at least for the early ones, there is like a meaningful difference. And my prediction for how you tell the difference is you look at the log prob of the overall model on the E token. Because if retokenization is happening, that log prob should be high. If retokenization is not happening, that log prob should be low, because the model didn't know what was happening going in, but it later figured it out. And I don't really know. This is like a bit messy to set up as a probing problem. You could just try filtering, like look at the histogram, see if it's bimodal, draw a threshold in the middle of the like log probs on E. Possibly the model will just always get it right because it's boring. I don't really know. I think an interesting thing we've not yet dug into, assuming you still have the energy. So we found these seemingly monosemantic neurons that detect, say, French and proto languages.
Right.
But I assert we've not properly proven monosemanticity. And I think it's interesting to dig into that claim and what this does and does not look, what this would and would not look like. Lol, he's so much cleaner than the rest. So, concretely, a really key nuance when thinking about these questions is, what is the data distribution you are studying the model over? Because we're doing probing, we need a source of supervision and labeling, which means we are not studying the model on like the full data distribution. But if you wanted to show that, say, the top thing is a German neuron, you'd actually want to be going even beyond the full training data distribution. You want to be looking at all possible inputs or something to see, would it activate on like anything that should be considered German and anything that should not be considered German. But we've only looked at Europal because the fuck even is German, man. And this is a problem because, as noted in part 2, superposition makes the most sense when you have things that are mutually exclusive, when both cannot co-occur. And so superposition is most likely to happen between two things that occur in very different contexts. And so when you look at a narrow-ish distribution like Europal, and you see that it looks really clean there, it could totally be the case that it also activates for list variables in Python or something, in a way that this just totally drowns out. A second problem is that, and this is like a broader problem, like there's a bunch of work looking at causal interventions, like the interpretability in the Wild paper that I did a separate video about. And I think that's a really cool paper, but it looks at how the model does a specific task called indirect object identification on like short sentences with a specific syntax. And this tells you a lot about what the model does in this narrow domain, but your hypotheses can very easily break when you go off distribution, especially since you don't know, if you're trying to look for polysemanticity and superposition, you just like, that's where all the dragons are. But this is like hard to solve because you don't know how to automatically label things as German or not. Like, what does German mean? And I think that an open problem I would really like to see someone pursue is trying to prove whether one of these neurons is or is not monosemantic. Anything you want to add to that?
Yeah, I should say, so we did do some follow-up analysis on at least the context neurons, which were in the main text. We ran, so we ran them over the full piled test set, as well as looked at the zero ablation over the full piled test set. And so one thing that you can do is you can then look at different subdistributions of the pile where you would expect French not to occur as much. So like, within GitHub documents, you would expect to see much less French than in, Europarl. And, as far as we could tell, when you looked at the max activating dataset examples, even in all of these other disparate distributions, they were all French. And so, we did go one extra mile in trying to conclude this. And so I do feel better about the result having done that secondary analysis. But again, as Neil said, the whole point of rare features, there could be like a 1 in a billion feature, which of course you're never going to find by just like looking at the max activating dataset examples, even, subsetted by a few different distributions. And so, yeah, this could be quite challenging in general to conclude.
Yeah, I think rare features is like a separate point from what I was making of just off distribution features, or like there's like potentially common but anti-correlated features,
right,
which narrow distributions will not show you, but plausibly can be found by like superficial things like your secondary analysis. And then there's the more insidious problem of things like rare features. It occurs in 1 in a billion tokens. How do you notice? Or there's questions of like, where do you draw the line for calling it monosemantic? Like, this thing is not literally cleaved at the joints by the thing we're looking for. It's like, well, there's like some stuff on this side, some stuff on that side. It's like pretty good, but it's not amazing.
Yeah, when we look into this, again, the sort of exceptions prove the rule in that a lot of the maximum activating negative examples are like idioms within like an English document or something, or the activations of like French names, which again, I guess this gets subtle. Like, is a French name in an English text, should that activate the French feature or not? And this goes again to like the thorny ontological question of like, what is French? And then a lot of the for the German neuron, a lot of the German where it doesn't activate is sort of similar when it's using like an English idiom or something, or often like at the very beginning of a sequence where it's a little bit ambiguous as to what language it's in still. Just circling back to the issue of rare features, another thing worth saying is that, well, of course, rare features are always going to be in superposition because it's never going to make sense to dedicate a single neuron to one of these super rare features. And so we should always expect these to be in superposition and therefore potentially confounding other monosemantic neurons.
Yeah. I just looked up the German neuron in Neuroscope, this website I made to look at max activating dataset examples for neurons. And the second highest is English text, English text, English text. Here in Germany, they often say, Frohe Weihnacht und einen guten Rutsch, something, something.
Yeah.
And it's like, well, German in the middle of text. Also, a lot of like random code. Like,
wait, really?
It's like code with German strings in it, and it activates on the German strings.
So like this is actually something which I've seen more. So like, yeah, you can imagine like, in all of these, there is a right tail. And so I have observed that like the most activating examples are in cases where the context, where it's like a shift in context. So like German in English text or German in code or something, where it's especially important for the model to be like, hey, actually, no, I'm in German now. Whereas like if the whole text is in German, there's already like a lot of residual Germanness that like exists within the representations of the model. And so it's less important for this neuron to activate. Whereas if it's a context switch, then it's like very important to be like, oh, no, I'm actually in German now. Like, please continue in German.
Yeah, if I can just briefly take over screen sharing.
Go for it.
To show people the weird-ass max activating dataset examples. So yeah, this is Neuroscope, my incredibly high production quality website. So we can see this like bizarre thing where it's got like, I don't even know what this is. It's like some kind of web dev format thing, a template that's like message ID, something, message string, blah, blah, blah. Interestingly, the quote mark starts activating, showing it's doing some kind of like in-context learning. And I don't know the fuck's up with that. It's just like, what the hell are these files? And then, yep, here's the German phrase. Here's some like actual German text. Oh, and then it flips to English. And then for a random English word in the middle, it's just like, doesn't look very German. This is more weird-ass code. Though, interestingly, this time it activates like immediately on the first one. And I have no idea how it manages that.
I'm
so confused.
Yeah, I mean, clearly there's at least one other document where this happens, and so there are probably a few.
But up here, it did not activate. And so I'm like, I'm interested. Here's another one. Here's another one. What the hell is this stuff?
Yeah, this is a broader lesson, and just like the pile contains a shit ton of random stuff. So any regex that you define will match against some cursed, terrible thing. And that in general, there are like lots of features. Oh yeah, this goes to another point, that there are just so many features that a model would have to represent to actually like predict all of this text correctly. And I think that there was like this, that there was the tiny models paper recently that showed that
tiny stories.
Yeah. That model is trained on like much simpler tasks. You could get away with much smaller models. And I think that they also seem more interpretable. But when you're having to predict this absolute mess, like, of course, the model internals are going to be cursed.
I'm loving that it's trying to figure out which start of line things are German.
Right.
It's like, no, those are German. Is a little bit German. Price,
Yeah.
nah. Can you give me the layer and index of another neuron? This is fun.
Okay. Layer 4, neuron 267 in Pythia 70M.
Oh, we should probably clarify these are all in the version 0 Pythia models.
Oh, yeah.
Because Eluther decided to upgrade the models in the middle of this project. And the Neuroscope is also on version 0, but I can't be bothered to update the text and everything because it's a massive pain.
627. Ah, there we go.
Looks Italian. Oh yeah, Neuroscope, I just concatenate a bunch of text together. Maybe unprincipled. It's so much more efficient, man. Yep. Lol. Nigeria and Sagu are insufficiently Italian. I'm loving that it's just so opinionated about which things are Italian. Hano. Hano is a great word. Yeah, this one seems really into long prose and not excited about people.
Arthur Miller.
Miller E. Marlon Brando. What? So many random English words. It gives up on in the middle. This is great.
Yeah, so this is what that left tail corresponds to, right? When you train these probes, or like, yeah, you count everything as being within the sequence, and so yeah.
Yes. Hopefully this illustrated to you that you can just take some of the many neurons in the massive JSONs on our GitHub and go look at them up in Neuroscope and screw around, see what you can find. I'm very curious. All right, so maybe to close, we want to talk a bit about follow-up work, open problems people can build on if they're watching this and they feel inspired.
Okay, yeah, so I think in general, like, all of the neurons which we looked at, you could look at in more detail, right? So as we were just saying, like, these monosemantic neurons that we claim are monosemantic, you could definitely try much harder to look over, fuller data distributions, try find rare features, et cetera, et cetera. I think, with our superposition results, you could try to be more careful about setting up the right type of causal analysis to show that these are actually causally implicated in some, retokenization role. Or in some detokenization role. Look for specific other types of motifs or neuron families within large language models, just as a way of kind of making more contact with reality, gaining much more traction. As we spoke about a little bit, sort of, going for looking for the output of tokens, or trying to probe for features of the output rather than the input, I think is interesting, especially for, studying these sorts of retokenization neurons. You could also imagine sort of looking at these neurons throughout training and sort of doing some analysis on like the training dynamics, to see if there's like anything interesting which emerges, and the Pythia suite being especially amenable to this.
Yeah, the Pythia models have about 150 checkpoints taken during training. I'd be particularly interested for the ones that showed interesting scaling properties, like the programming language models, the programming language neurons, then small models, they don't have dedicated things. In like multi-large models, they do. If you look in the large model over training, is it emergent to have a single neuron on this? Or the factual knowledge stuff? I'm like particularly interested in whether emergence across scale is the same as emergence across training, or if it's something importantly different.
Like lottery tickets or something.
Yeah. And that was really checked.
Yeah. And yeah, so the TLDR on that is just like doing everything we did, but just like actually more rigorously. Like, I think, in some sense, I think in like past probing studies were, even more just like, oh, wow, these features exist. And then, we took one more step of being like, oh, no, they exist. And like, here are some like interesting facts about these particular neurons. But there was still an aspect of breadth to our work. And so I think, there are many follow-up studies, which could be like narrowing in on something and really, really just drilling it down in as much detail as possible, going all the way down to the weights, being, extremely mechanistic, and yeah, just really optimizing for depth.
2 points on that. Just diving deep into something like the French neuron and trying to really show that it's monosemantic by either just showing it's really rigorously monosemantic, like full data distribution, studying ablations, figuring out how you might look for rare features, looking at how it's used mechanistically, like which things compose with it, what changes when you ablate it, what activates it, and what features get input into it that matter. Like, is it really accumulating like 100 small pieces of evidence? Finally, trying to zoom in on the detokenization neurons. I'm like particularly interested in whether you can really understand how something is represented in superposition as a precise linear combination of neurons. Like we found, 3 neurons, you add them together, it kind of works. What does the right linear combination look like? How sharp is it? And in particular, can you learn a direction that corresponds to how it's used in the model rather than just corresponding to what it looks like? Can you ablate the direction such that it systematically damages model loss on the social security text, for example? What does that look like? I don't really know. Sounds fun.
Yeah, and then I think somewhat orthogonal to the sort of lower level of methodological details is you could just imagine trying to come up with data sets for features which are like more relevant than just like whether or not a current token is a verb or not. One concrete example of this is we tried to probe for a falsehood neuron. This is like when the model sort of like sees a lie or something like this. And the way we did this is we trained on we used the counterfact data set from the original Rome paper, which had sort of a series of true completions and false completions, and trained a probe on that final token to classify whether or not it's true or false. And we did not find sparsity in these probes, so there were not sparse probes which got good performance on this task, though there were dense probes which got like classification accuracy ballpark of 0.9. And so I read this as like more of like a dissonance or confusion feature of like the model saw like kind of an anomalous continuation or something which it was somewhat unexpected, rather than which has like all sorts of correlates and is not sort of compactly represented. But you can imagine other sorts of more carefully curated data sets that like look for like more specific behaviors around different types of lying, deception, certain types of planning behavior, also just more generally things having to do with like bias or fairness. So like, we showed lots of neurons which like encode for particular attributes of people. It might be interesting like how these features are both like constructed and used downstream. And so just more generally, like thinking about higher relevance features which are more relevant to all sorts of risks and harms that we're concerned about.
Yeah, one thing that you could possibly try doing is just find neurons that classify toxic versus non-toxic text and delete those, or try ablating the sex and gender tracking neurons and see how this changes the model's behavior in various fairness relevant contexts.
Yeah, although sex and gender in particular seems to be a very or like a sort of loud feature, and that there are clearly many neurons like in all layers which seem to respond to it in some sense. Although you'll note that this is primarily concentrated in the early layers.
Makes sense. Oh my god, layer 12. It's intense.
Yeah.
Oh, that's so intense. Anyway, yeah, that makes sense. Generally, like, what does true model editing look like when based on interpretability is an interesting question to me. And in particular, what does surgical model editing look like? Like deleting a neuron to remove a model's knowledge of a feature seems super interesting to me. Can we do some kind of threshold ablation where we set the neuron to 0 if it exceeds like 3? And can that let us erase knowledge of French while preserving knowledge of everything else even more? Why are there like 50 French neurons? Can we differentiate them better? Is their meaning covered by the larger value of the neurons, or if you round all positive examples of French to like 6, does that preserve performance? Is another interesting question.
Yeah, if you just like collapsed it to its mean, for instance,
Yeah, exactly.
On French or not, would that preserve performance? Or is there something in the activation range which is relevant?
Yeah, possibly some kind of like actually redundant representation. I don't really know. More generally, I kind of feel like the story of this work is take a mildly interesting technique, then go and do a lot of detailed case studies trying to find weird shit out about the model.
Yeah.
I think there's a lot more we could learn from more case studies, both digging deeper into these, and in particular, I'm excited about retokenization case studies. What else can you find if you just pick a model and go wander around it?
Yeah, and I think that this is a different style of science than many people from like conventional ML backgrounds are used to. That this is a much more observational style of science that is like more reminiscent of biology or neuroscience. And I think I know, yeah, some people in my academic community has like I remember being asked like, what is a result here? Like how do you what does a contribution look like? And I think that, yeah, depending on what and so I think depending on the community or mindset you're coming from, it can be helpful to sort of just try and adjust and think about a different style, a more observational and empirical style of science.
Well, I guess observational in the broadest possible sense, where we can do a fuck ton of causal intervention internally.
Sure.
But we're not making GPUs go brr. Instead, we're making CPUs go brr. As you train tens of thousands of probes.
Yeah.
But yeah, to me, one of the core things of mech-interp is having the potential to be surprised by what you find. I sure feel surprised by what we found here. So yeah, thanks all for joining me.
Yeah, thank you.
I hope people enjoyed this extremely in-depth tour of finding neurons in a haystack.